Now we're talking about the binomial distribution, and this is going to be an important topic that we're going to cover. This will definitely be on exams. It's something that you need to know how to do just off your head, and it'll take some time to learn, but we're going to walk through it now. So go ahead and pause the video and write this down, and then I'll finish writing with the formula here in a second. Alright, the binomial probability distribution function is the probability of obtaining X successes in N independent trials of a binomial experiment is given by the following. So, already off the bat, we're telling that X means the number of successes, N is the number of independent trials, and so here, this is how we would write it. We'd say the probability of capital X equal to little x. So this is saying the probability of our random variable capital X is equal to whatever value we want it to equal to. If you think back to the basketball example that we did, we would say the probability of capital X, which means the number of free throws made, is equal to 0, 1, 2, or 3. And then we would just say equals the probability. So here, this is equal to, and this is quite long, so maybe watch me first. Alright, it involves the combination formula that we looked at previously. So that's the combination. Earlier we had R instead of X, but it can be any letter that we want it to be. Then that's multiplied by the probability of a success raised to the X power. So that's saying the probability of a success raised to how many successes that you want, and then that's times 1 minus P, which is the failure rate. So 1 minus the probability of success equals the probability of a failure. So that is raised to the N minus X. And we'll break down this a little bit more. So N is the total number of trials, and they have to be independent. X is the number of successes that we want to happen out of those N trials. So N could be 100, and we want to know what's the probability of getting 30 successes. So then we write the probability of getting a success, and we would raise that to 30. And then we'd want to do 1 minus the probability of success to get the failures, and then N minus X, that would be 100 minus 30, so 70 failures. So if you were to add these exponents together, they would equal 100, which is what our N is. And there's going to be some, we're going to have some more definitions down here below to help explain this some more. So here are some very helpful bullet points that you'll need to know. A binomial experiment. And here are 4 bullet points. Consists of N trials, meaning the same action repeated N times. And these do have to be independent. That will be our second bullet. The trials are independent. Remember what independent means. It means the outcome of one trial does not affect the outcome of the next trial. So for instance, flipping a coin, that would be an independent event because I flip the coin one time right now and it lands on heads. That's fine. Then I pick the coin up and I start to flip it again and it lands on whatever it lands on. But the first flip did not affect the outcome of the second flip. Same thing with rolling a die. I roll a die one time and I get a 2. I roll the die a second time and the first time I rolled it didn't affect that trial. So that's what we're looking for with independent, and we can write that the outcome of one trial has no effect on the outcome of another trial. Third bullet, each trial has two outcomes, so that's important. And meaning by outcome, it means a success or a failure. So each trial has the same two outcomes: success or failure. And we get to define what a success and a failure are. And the fourth bullet point, the probability, the probability of success, P. So the probability of a success, P, is the same from trial to trial. Alright, so this is very important information to know. You will have to know this formula. You will need to know all of these bullet points. So let's look at just a brief example of what's going on here. Alright, example 1. Toss a coin 3 times. What is the probability of 2 heads? And I abbreviated probability as prob there, just to save some time. So we're tossing a fair coin. I didn't write fair. It's a fair coin 3 times. What is the probability of 2 heads? Well, here, let's first list out all the options before we get into the binomial formula. This is a binomial because we have a success and a failure. The success here would be the probability of heads, and the failure would be the tails. And we have N, which is 3, all right? And then we have P, the probability of success, which is 50%. So all that's laid out there for us. But what I want to do is list all the possible outcomes and show you that the two align. First, write a list. All right, let's write a list of the potential outcomes here. So we can get a heads, 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 tails, heads, tails, heads, heads, tails, tails. And then we can have a tails, 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 heads, tails, heads, tails, and tails, heads, heads. So, well, this is all the possible outcomes of flipping a coin 3 times. Now I want to know what's the probability of 2 heads, exactly 2 heads. So we come in here and we find the combinations that have 2 heads listed in them. 1, 2, 3. So there are only 3. So what way we would write this, we'd say the probability that capital X is equal to 2, meaning we should have defined X up here. Say X is equal to the number of heads. So now this X means number of heads. The probability that the number of heads is equal to 2 is equal to, well, how many did we want? Or how many outcomes are the ones that we want? 1, 2, 3. That goes on top. And the bottom is the total number of possible outcomes, which is 1, 2, 3, 4, 5, 6, 7, 8. 3 eighths. All right, now we want to notice that this is a binomial. And so this is a simple example that writing a list out is easy, but we're going to get into much more complicated. So what we want to do here is we want to say the probability that x is equal to 2 is equal to, and let's write our formula. Always write our formula, and that will help you to know what you need to plug in. So we have the combination of n and x times the probability of x times 1 minus p to the n minus x power. Alright, now let's fill in everything that we know. N is the total number of trials that are to be repeated, and how many times. So 3, we're doing it 3 times. Combination of x, and how many probabilities do we want? Your x is this number here. It's given to you with what you're trying to find, 2. Times p. P is the probability of a success. A success here is flipping a heads. So the probability of flipping a heads is 1/2. So 3c2, and then times 1/2 raised to the x power. X we just found to be 2, and then that's multiplied by 1 minus p, which is 1/2, and that's raised to the n minus x power, which is 3 minus 2. Alright, just to kind of go over what we just did, we said n is 3, because that's the total number of trials we had. 2 is our x value, the total number of successes. It tells you right here what you're looking for, and it tells you in the problem that x is 2. P is the probability of a success, which is flipping a heads, which is 1/2. And then this is 1 minus p, or the failure, so 1 minus 1/2, and then that's raised to the n minus x power. Alright, and then now simplifying this, just do it in steps. This first part, the combination, it's 3 factorial over 2 factorial times 1 factorial. So I skipped a little step there, but if you need to write that step out, go ahead. And then 1/2 squared is 1/4, and then this becomes 1/2 to the first power, which is just 1/2. So I skipped a few of the intermediate steps, but please work out those steps if you need it. You simplify this and you get 3/8, which matches what we just found over here. So there, I'm just showing you how these things work. All right. Now let's determine if a scenario is a binomial distribution. So here's example 2. I'm just going to say binomial or not. And here's part A. A basketball player makes 80% of his free throws. He is asked to shoot 3 free throws. So what we want to do is determine if this is a binomial or not. And yes, it is. So you can kind of go down the 4 bullet points that we talked about and kind of go through those. But yes, because each free throw is binomial, meaning there's only the same 2 outcomes every single time. It's either a make/miss, which could be classified as our success and our failure. N would equal 3 here, and they're all independent, and independent, because each time he shoots a free throw, he has an 80% chance of making it no matter what. The previous shots don't affect any other shots. And then each trial has, so same thing I just said, each trial has the same probability, P equals 0.80. Alright, so it's important to be able to distinguish between what is and isn't binomial. So let's look at another. 3 cards are drawn from a deck without replacement. And the number of aces is recorded. So we need to go through our bullet points here and determine if this is a binomial or not. So we have N, we're drawing 3 cards, but we need to see if the trials are independent and if the probability is the same from trial to trial. So that's where we run into a problem because it says without replacement. So this is not binomial because the probability of an ace on the first draw is 4 out of 52, but it's different on the second draw. Alright, it's different because we're doing this without replacement. So we take a card out. Now we no longer have 52 card. We no longer have 52 here on the bottom. This will now be 51. So what I mean is, if first card is an ace, then probability of ace on second card is 3 out of 51, which is different. That's the issue here. And even if it wasn't an ace, you'd still have 4 out of 51, which is a different probability than here. So we're gonna, this end of this video, we're gonna look at another video where we actually will start looking at some problems that you will see on the exams. We'll start looking at some real life examples and how to find expected value and standard deviations.